Hello everyone. Today we are going to talk about convolutional neural networks or CNNs, which are a type of feed-forward network and they are mostly used in computer vision and image processing. Okay, they have other applications, but mostly convolution is used to detect features off of an image. So what you see is we feed them the input images, let's say, and then we perform a convolution. If you don't know what convolution is, I have a video on my channel under playlist Computer Vision Image Processing, which is convolution and linear filtering. Take a look at that. Which is basically, as it says, it's a filtering. It's a way to detect the specific features. Like, for instance, if you have a vertical edge detector, right, something like this, then in a face you can, let's say, detect the nose. Okay, and if you have a horizontal edge detector, right, something like this or this one, then you might be able to detect, let's say, the lips, the eyes, the eyebrow and stuff. Okay, so you apply these different filters to the image and you get a bunch of features. Okay, so all of these basically convoluted images are the type of features detected in one of them vertical edges, maybe in the other one horizontal edges or anything like that, in one of them a corner of any picture. And that's basically the same as what you do in Haar cascade classifiers, which are used for face detection. Again, I have a video under the same playlist, Computer Vision Image Processing, where I talk about Haar cascade classifiers. So basically they use this kind of filters for convolution, and based on the result of that they detect basically faces. But these convolution neural networks have more application than just faces. They can use for so many different things, in general for object detection and so on. So that's the first thing you do. You detect a bunch of what we call low level features. Okay, and then since the images have tons of pixels and tons of information, you have to use downsampling or subsampling and reduce the size of the images. Because if you have a simple HD image, right, a simple one that is only 720 by 1080 by 3 channels, red, green and blue, then you have more than 2.7 million values. Okay, and that is a lot of information for the neural network to process. So use a subsampling, sometimes you might call it a pooling, and we'll go through that. And you reduce the size of these images, then you apply another set of filters, another set of convolutions, and this time more. So now because you started with more images, now if you apply even the same number of filters, you're going to get a lot more features. This time these features that you detect are more face-like. So now you go to what we call higher level features, more of them, smaller, and of course because they are smaller, basically the size of the filter, we'll talk about it, is going to be closer to the image size compared to original, right? So originally you see that the size of the filter here, this small square, is much smaller than the image. But now if you look at the filter size, I mean not this one, okay, this original one, you can see that the size of this square and the image are not comparable. But as you get further down, you see the size of the filters are closer to the images because the images are shrinking, not the filters. So now these are basically containing more information about the entire image, and they are higher level features. And you can keep doing that until you get to the last part of downsampled convoluted images, which are very much face-like, and then you can connect them to the dense layers, fully connected layers, and at the end you might have a softmax function or anything to detect different classes. Okay, so now one of the big advantages, you might say, why did you use a convolution? Why didn't you use the dense layers right off the bat from the beginning? The problem is the number of weights that you need. Okay, as I told you, if I start with a simple HD image, there are 2.7 million, more than 2.7 million pixels, or values, not pixels. and each one of them counts as a feature. So if my first layer is a dense layer, I need to have at least 2.7 million weights plus a bunch of biases, right? Just to go from the image to the first layer, to the end of the first layer. And that is a lot of weights, okay? That's a lot of weights to train, right? But on the other hand, if I use convolution, so let me bring this down, compare this against now, let's say I use some filters here. And let's say the filters that I use are 6 filters, right? So here you see I got 6 images, so I have 6 filters. And these filters are typically small, as we'll see. The size of them are like 3 by 3, 5 by 5, 7 by 7. So each filter has 7 by 7, 25 values, and then 6 of them you get 150 weights, 150 values to update as compared to 2.7 million. So what we call the weight sharing, right? All of these basically values in this first layer, in this first feature map, are using the same filter, the same, let's say, 5 by 5 values. So this weight sharing is what makes convolution neural networks much more efficient, because we are using much smaller number of weights and biases. So we can train them faster, and since you don't have a ton of weights, then you are not overfitting as much as a dense layer does. Okay, so it is very, very important. We typically, as we go through the layers, you saw that we have more features and smaller sizes. Most of the time we increase the number of features by a factor of 2 and reduce the size of the images also by a factor of 2, but it's not a mandatory thing, but it's quite common to increase the number of features, reduce the size of the images. Okay, now I said in the beginning that these convolution neural networks are used in computer vision, and they kind of revolutionized the field of computer vision by making them less expert knowledge required. What does that mean? Well, in the past, we had, as I said, stuff like this, like hard cascade classifiers and others designed for computer vision. And the thing is, these filters, you see, these filters, these edge detectors and so on, or corner detectors, they were custom built for different things. For, as I said, for faces, vertical and horizontal edge detectors are really good. For other objects, they might be something different, right? So these filters, they had to be custom designed. They have to be manually designed, and in order to design them, you needed knowledge in image processing and computer vision, okay, to do that. The good thing about these convolution layers is the shape of these filters that you use here or here and so on, these you don't start with something like this right off the bat. You start with some random numbers. So I use 3 by 3 or 5 by 5 filters. But initially, I fill them with a bunch of random numbers. So in the beginning, my filters will not look like this at all. Okay, they're going to be just a bunch of black and white pixels. But as the network tries to learn to distinguish between all of these basically target values, what happens is the network will learn what kind of features it needs in the first layer, in the second layer, and so on. Okay, so you don't need to design the filters anymore. The network will learn the shape of those filters. So if you do that for face detection, the kind of filters that you get in the first or second layer will be different than, let's say, if you want, for instance, I don't know, some tomography or something like that, or some, let's say, detecting different kind of, let's say, flowers or something. You will end up with different types of filters, okay? So now with the CNNs, you might be able to train a network to perform a perfect or very good classifier without being expert in computer vision. And that is one of the big advantages of CNNs. Okay, now what kind of size of filters would you choose? Well, this is up to you. It's in general like a hyperparameter, but we use small filters, okay? We don't go with big filters. And we size of the filters, we use odd numbers and make sure they are square, okay? So 3 by 3, 5 by 5, 7 by 7. You are not, I mean, you can if you want to, but that's not a custom in convolution neural networks. You don't pick a 4 by 6 or 8 by 10 or something, or even 8 by 8. You typically use an odd number, and the reason is you have a middle, a center, okay, for your filter, right? A center row, a center column, a center point, as opposed to 6 or 8 that don't have exactly a place for that. And you choose them square, it's much easier to do with the squares. Okay, now as I said, and let me emphasize that one more time, the CNN learning is basically has a hierarchy. What does it mean? Means at the lower, at the layers, at the first layers, you're going to learn lower features, lower level features. And as you move toward the end of the convolution layers, you learn higher level features. And these higher level features are bigger in size. They are closer to those images. The lower level features are smaller compared to the image. And the reason for that, as we saw, was the images are what? Shrinking in size. So that's what the reason is, and you can see it here too, right? The image size is shrinking, the filter size is staying the same. So the filter size, or the convolved result, the size of it compared to the original one, is getting bigger and bigger, and so it can have bigger features, more general features, more higher level features, as opposed to some edges or some corners. Okay, so this hierarchy in CNN learning is very important. Now remember that I said you do subsampling and you reduce the size of the images. Another name that is very common for it in CNNs, in the language of machine learning, is called pooling. Okay, so pooling is another name for reducing the size of these images. Now, how would you do it? We typically either do it by max pooling or average pooling. So what is max pooling? So let's say here, if I want to reduce the size of image by 2, then I look at each window that is 2 by 2 in this convolved image, and then between these 4 values, right, inside this 2 by 2 window, I pick the max. So in this orange window, I pick what? I pick 6. In this green window, I pick what? I pick 8. In this blue one, I pick 3. And in the gray one, I pick what? 4. Okay, so this is called the max pooling. But if I want to do average pooling, then I have to take average. So here it's 11 divided by 4, right? So it is what? It is 2.75, correct? And then the other numbers too. So here you have 5 and 14, that's 19. So if I do it for here, it's going to be 4.75, and then for these 2 bottom ones, it's going to be 1.75, okay? So I can do either one, but the max pooling is more common, and the reason for that is this. So the goal of these convolution neural networks is to what? Is to detect the feature. Remember, we said the goal is to detect these features. So when we apply these filters, we want to say, hey, in this window, I found the nose, I found the vertical feature, or I didn't, right? So now, if you come here, and in one area, you found some feature, and the neighbor areas right next to it, I say, hey, I didn't find it, then which one would you pick, right? Would you say I did not find it in this bigger window now? That nose is inside this bigger window, or it's not in? So you want a yes or no. You want a 1 or 0, found or not found. So if I pick the maximum, which is found, then I say, hey, I found it, right? But if I take the average, then it's like if I say this found is 1 and the not founds are 0, it's like, hey, I found it by 1/4, right? Which if you want to round it, it's like not finding it, right? So it's better to pick a max because you want to pick something if it's there instead of being affected by the neighboring windows that might not have that feature and just denying that this guy exists. So that's why max pooling is more common than average pooling. Another terminology that I need to talk about is called strides. Strides means how much each window is moving when the convolution is being done. Okay, so when you do convolution, remember that here is your window, and then when you want to move it to the next position, you might move it such that it has no overlap, so it's just touching the previous window, or you might move it such that it does have overlap with the previous window. Okay, if that's the case, then means the stride, the amount of displacement that you have, is less than the size of the window, so you will have overlap. And if you do that, that will reduce the size of your image. How? Let's take a look here. So here is an image 7x7, and the filter we use is 3x3. You can see in the red window. And the stride here is 1. You see that it only moved 1 pixel. And if you see, there are 2 pixels of what? There are 2 pixels of overlap. And so here, the value of convolution between the red window and the part of the image under the red window will be stored in this red pixel. The one for the green will be in the green pixel. And as you move forward all the way to, let's say, here, then it will be stored in this blue pixel. And between the red one and the blue one, you see that the window has only moved 5. So the size of the final image is 5. And 5 here is 7 minus the 2 overlap. Okay, so you see I could reduce the size of the image. And if I use, if the image is a little bit bigger and the filter is bigger and I choose a very small stride, I can even further reduce it. Okay, so if this guy was instead 11 by 11 and I use the same size of the filter, right? Or maybe this time I use a 5x5 filter. Let's say I use a 5x5 filter, and again I use a stride of 1. So now each window with the next window will have 4 overlap, and 4 overlap means now you're looking at 7x7 output. Okay, so you see you're kind of getting close to half size and so on. So a convolution layer with strides can do the job of convolution plus subsampling. So you can either use this one or this one, while most of the people, since they don't want to do all these calculations and see what kind of filter size and what kind of stride they should choose so they get half size, most of the people will typically go just with convolution and subsampling and do it in 2 different steps. But that is a terminology I wanted you to know. One of the things you need to use is called the flatten layer, okay? And that happens right before you pass them to these fully connected networks. If you see here, my results right before going to the dense layers are still images, and they are matrices. But these dense layers, they expect inputs P of dimension n by 1, not m by n. Okay, that's what these guys expect, but here I have m by n results. So what I need to do is to flatten those images or vectorize them, convert them to a vector so they can be multiplied by those w's, okay, which are also vectors. So we need to use a flatten layer, right before the dense layers and at the end of the convolution layers to make them appropriate size. Okay, So this is the essence of convolution neural networks. And then we have these dense layers to to combine those high level features with proper combinations, so we can have like the best class out of a softmax function if we are doing a classification. One last thing before we go to my TensorFlow code is sometimes the images that you pass to a network, they are of different sizes. Now, if you use standard databases, that's not what you get. You get all the images the same size, but sometimes they are not. Sometimes you're collecting some of the images yourself. You are training a network that does not have external database for it, and because it's a special class of objects that you want to train yourself. And these images that you got, some of them you got from the web, some of them you got with your phone, some of them you got from somebody else, from a professional camera. And either you have to sit down and resize all of them to the same size, which is very time consuming, or there should be something in these neural networks, some kind of layer that will take different types of sizes of inputs and still being allowed to manage and work. And that is called global max pooling layer. What is that? So here, if I have the previous layer to the global max pooling, and these are like a bunch of h by w by c, right? And h at w is the size of these features, and c is the number of these features. Then if you use global max pooling, it's not going to do it over these windows inside each one of them. It's going to do it over the entire set of these features. Okay, so basically it will convert the size of these h by w by c's to 1 by 1 by c. Okay, yeah. So basically it will convert each one of these convolved images into a size 1 by 1. Okay, it's a global max in the whole image, not over each individual local window. So you only get a 1 by 1, and it's either find or not find or something like that, and you convert that whole thing into a 1 by 1 by c. So now if I have something just similar to this, right, and this time instead of this w by h, it's something else like h prime by w prime by c. Doesn't matter. This time still you'll get 1 by 1 by c. So it doesn't care what are these input images, the size of them, it will convert them into a 1 by 1 by c. So if I have one set of these and another set by hw, the result of those and these ones are all the same, 1 by 1 by c, and since they are all the same dimensions at the end before going to the dense layers, they can be combined together, they can work together. Okay, so if you have different images at the end, you might use a what instead of one of these local subsampling or pooling. At the very end, you might use a global one. So when these different inputs with different sizes come in, at the end, all these results will be the same before going to the fully connected layers. Okay, so now let's go ahead and look at the TensorFlow code. Here we do image classification, and we do it on the set of data called C410. Okay, so we have more than 2 classes, and 10 means there are 10 classes of objects. What are these? So if you look at C410, which is published by Canadian Institute for Advanced Research, there are 10 classes of objects: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and trucks, and there are lots of images for them. The size of these images are 32 by 32, so they are highly pixelated and they are not really high quality images, but they can be. But the good thing about them is they are color images. Okay, so they are not just black and white, they are color or grayscale. They are color images, but again, they are small, and there are 60,000 of them for training, something similar to MNIST. So it's not really easy to distinguish some of them. I mean, if you look at these different pictures of dogs, not all of them would definitely look like a dog. Okay, now car is probably easier. Airplane, I mean, look at that. It's very hard to say if that guy is really an airplane, right? Let's see if there is a bigger picture of this. That's here, we can see. And let me zoom in, right? I mean, look at that. That is very hard to say that's an airplane, even if you give it to a human being. And that might, but again, if you look, some of these are not easy. Or look at these birds. Look at the diversity of them. Or some of the cats. I mean, this is very hard to say what it is. Okay, very hard. Or you see here, let's say this one. I mean, it can look like a dog to you. Okay, so they are not high quality images, but again, this is very common. It's kind of like a benchmark. So just wanted to show you that. So we're going to work on these, and the good thing is these images are available in TensorFlow. You don't need to download them. You can just say CFAR10 is tf-keras datasets.cfar10. You create the object, and now use the load data method of that object to get your X and Y train and X and Y test. Okay, so you don't even need to split it into train and test. It's already train and test split itself. So it's really convenient to use these. Now, the size of the X train is what? It's N by W by H by C. What is that? N is the number of pictures you have. W by H is the size of the images, 32 by 32, and C is the number of color channels, which is 3. Okay? If these input images are not color images, if they are grayscale images like MNIST fashion, and MNIST fashion is similar to MNIST, but instead of numbers, they are on basically clothing. Okay, so you can see that MNIST fashion is on different types of clothing, but again, they are black and white and the same size as MNIST. So if that's the case, then you need to change. You need to add a dimension of 1 to it, because what TensorFlow convolution layer expect from you is a set of inputs with 4 dimensions, where N is the number of the images, W by H is size of the images, and C is the color. If you bring the MNIST fashion, you are missing this last one, which should be 1, because you only have 1 color, right? It's just grayscale. So you don't have that 1. If that's the case, you need to do something like this. You have to say X train equals NP numpy expand dimensions of X train and -1. What does it mean? It means convert this into what? Basically, it means convert this into this. Add a 1 to it. Then you can use it in the neural networks. Okay, so again, if it's grayscale, you have to artificially add that extra dimension of 1 using this technique. Okay, so now that we got the images the right size, the next thing we need to do is to bring the range of the images from 0 to 255 integers to 0 to 1 double or floating. So here we divide all of the train and test images by 255 with a decimal. So now the range of these numbers are going to be between 0 to 1, and they have floating points. And we can see the shape of them if you want, right? So here you see when we run this, it downloads all these images, and look at the shape of the training images. You see 50,000 training images and 10,000 what? Test images. As I said, you have a total of 60,000 images. Okay, so these are the kind of images that you will get. And the other thing is the training, Y training or Y test, the targets, they should basically only have a what? They should only have a dimension the first dimension, they should not have this artificial 1. So it's exactly the opposite of what you had for the x values, for the training values, right? For the inputs. The inputs need to have 4 dimensions, the output don't. So here, if you look, when I look at the shape of y train, the shape is 50,000 by 1. So I need to get rid of that 1. How? I use the flatten thing. I use the flatten command on the y train and y test, and that will get rid of that 1. So now you see the y test and y train don't have that extra 1. Okay, so now these y's are the proper size as well, and clearly you see if I look at the number of different distinguished values, unique values in y train using the set command and then the length, it gives you the number of classes, the number of classes of images, and as we expected, there are what? 10 classes of objects, airplane, car, and so on and so forth. Okay, again, this command set will give you the unique values in y train, right? So if you have a ton of 1s, it just counts them as 1 time. If you have a ton of 5s, it just counts them as 1 5. And so this set will convert all of those 50,000 values into only 10 values, and length, of course, give you 10. So this is bringing the data in. Now we need to form your convolutional neural networks. And as I said, you can either use convolution and pooling, or you can use strides. So here, this top part is with the strides. So you create a sequential neural network. And I use a filter size of 3 for the convolution. So the convolution layers are called layers conv2. And how many of them do you need? So for the first layer, I use 32 filters. They are all size 3 by 3. I use a stride of 2, so reduce the size. And the activation function we typically use for these are ReLU functions, okay? So these are not just pure convolutions, they are convolutions passed to an activation function. If you don't want activation function, then you can skip this part or use a linear function. But typically we use the ReLU to include the nonlinearity. Okay, so this is one way to do it. And you see when I go to the second neural network, second layer, I use 64 filters, and then the next one I use 128. As I said, each time you typically increase the number of filters by a factor of 2, and these strides will take care of the pooling for you and reduce the size by a factor of 2 for you, okay? And then once these 3 layers of convolution is done, use the flatten layer as I told you. You can use dropout layers. I explained them a little bit in the past. These are to basically improve generalization and avoid overfitting, and this is the chance of any neuron being set to 0 and being ignored. So here I use a dropout right before my first dense layer, and for my dense layer I use 1024 weights, again ReLU function, the dropout again, and finally my last layer, which has the softmax function because it is classification, multi-class. And how many basically weights do I need? NC, 10, because I have 10 classes, so I need 10 weights. Total of 10 weights and 1 bias. Okay, so this is one way to define your neural network. Or you can go with the max pooling and avoid the strides. By the way, you remember that we also, of course, in the beginning, we need the inputs layer, okay? We definitely need the inputs layer in the beginning, right? You cannot avoid that. And so we use the input layer in the beginning, and for the shape of that, you see I'm using xtrain, the first dimension shape. So basically, not the first dimension, the first element in xtrain.shape, which is basically what 32 by 32 by 3. Okay, that's the shape of the first picture in the training set. So I use that shape so the input layer knows what kind of input it should be expecting. So that was with the strides. This other one, as I said, use a convolution layers and don't do any strides in it, right? followed by a max pulling 2D where the pull size is 2 by 2 to reduce the size by 2. And then for stride, you can use strides for a max pulling 2 if you want, but we don't, so we say none. And for padding, we can have padding or not padding. If you don't want padding, you say valid. Valid means I don't want padding. If you say same, then it will add paddings for you. We don't want paddings here, so we skip that. So you see, convolution max pulling, convolution max pulling, convolution max pulling, then flatten, then drop out, dense, drop out, and dense. This is basically doing something similar to the top one. So now that the neural network is made, I need to add my optimizer. I use Adam. For loss, remember we said this is classification multi-class, and we might have a bunch of zeros. So we use categorical cross entropy, but we use the sparse version of it. And for metrics, we use accuracy. And then we use the fit to train the model with xtrain and ytrain. For validation data, we use xtest and ytest, and we pass to it the number of epochs. Here I use 25 epochs. And you see that the loss function is going down, the accuracy is going up. And the fact is, it does not do an amazing job. It's not bad, but it's not as good as you expect. I mean, the accuracy is about 82%. Okay, it doesn't go like 95, 96 or something. And your loss is still big. If you plot the history of the loss and the loss on the training set and the testing set, val loss, this is the kind of thing that you see. Okay, so you might say, well, let it go down more epochs, and I tried that. I used 40, 50 epochs, and these epochs, by the way, are very time consuming. Okay, you definitely want to run it on GPU, and it goes down, but not more than like 84 or 5%, okay? And you can see here on the testing data, it's kind of flattened already. And when it's flattened and this training on the loss function on the training data is going down, that's a sign. What sign? Yes, that's overfitting. Okay, so if this guy is going down, means you are fitting better to the training, but I cannot generalize it to the testing. Means I'm basically fitting the noise, I'm fitting the small changes in the images, which are not as important. I'm not capturing those global features. Okay, so when you see the test data is flattened and not the training, you're definitely doing overfitting. And here I used a big dropout, okay, and to avoid this overfitting, but still it is doing it. And one of the reasons I told you is because of this quality of the pictures. It's very hard for it to detect some from the others, okay? They are very low pixelated, small images, and so it might not do a super amazing job. So can we do other things to improve that? Yes, that's what we see in our next video. We can use batch optimizer layers and data augmentation to improve the performance of our CNNs, and this is the accuracy. As you can see, again, you see the accuracy is not going up, but on the training it does. Okay, so and if you want, you can use the confusion matrix. Here is the confusion matrix. You see the diagonals are big, but here off diagonals you have some big offsets. I mean, look at that. 224 compared to 467. These are the correct detections. These are the wrong detections. All of them, all of these off diagonals, okay? And that means class 3, right? The true label is misdiagnosed as class 5. And if it's the same as this one, actually 3 here is 4 because you're starting from 0. So class 4 is misdiagnosed as class 6. And you see class 4 is a cat and class 6 is a dog. And if you looked here, you saw that, yes, some of these cats and dog pictures are not that good, right? Let's go back here. You see? Look at some of these cats and look at some of these dogs. And even if you give it to a kid or maybe a grown-up, they might not be able to detect this. I mean, this to me looks like a cat, or this might look like a dog. Okay, so some of these images are not really, if you look at these dog images, many of them are not that good. Look at this one, look at this one, look at this. They're very hard. Look at this one. Okay, only some of them are very prominent. So it's no surprise that in those two categories, it did not do an amazing job. But in the rest of them, still not amazing. But in these few categories, okay, you see these highlighted numbers, they are very bad. So in the next video, I'll show you how we can use data augmentation and we call batch normalization layers and data augmentation technique to give the network more data and to make it do a better job than 80% or 82% accuracy. So thank you so much for your attention. I'll see you in the next video.